All right, in this video we're going to begin to explore something called a rational function. So we did detail that a rational function is a type of function and its parent function is just the function 1 over x. So that's the function that we're going to begin dealing with. All right, so we're going to first talk about the domain of this function. And remember that the domain is just the possible input values. So when we talk about what's allowable or what's possible, we have to ask ourselves what would make this thing either undefined or imaginary. So we have two cases here, right? This could be undefined under some circumstances. It can't be imaginary because the only way you can get an imaginary number is if you take the square root of something that's negative. So this is not going to be imaginary, but it could be undefined. So when is a fraction undefined? Well, if you divide something by 2, that's okay. You'll get a half in this case. If you divide 1 by 1, you'll get 1. That's nice too. Even if you divide 1 by 0.5, right? 1 divided by 0.5, that's okay too because you have 1 divided by 1/2 really, which is the same as 1 times the reciprocal. All right, so I can even divide by fractions. What I can't divide by is 0. So 0 is not allowed. All right, so what I'm going to say in this case is that my domain is all real numbers when x is not equal to 0. Okay, this is how I would write that domain out. A couple other ways to write this. You could say, alternatively, that your domain is from -infinity to 0, not including 0, and then again from 0 to infinity. All right, this is an alternative way to write the same exact thing. This is just saying that I can use all the x values from -infinity up until 0. I can't use 0. And then from 0 again until +infinity. So this also says all real numbers excluding 0. So a couple ways to write that. But it's important that we recognize that the denominator of these rational functions can't be 0, because if it were, then we would have an undefined expression. So what does that mean for the function's behavior? And I just want to sketch that function right here off to the side so that we have a good picture of what these rational functions look like. If you were to graph this function, you would get something like this. So I'd like you to sketch that in. We're going to call this the function f of x. All right, I haven't really labeled anything too clearly here, but there is something about this graph that should be standing out to you and be pretty unique. And that's the fact that right down the middle, the function doesn't exist. And that's because when I plug in 0 for x, I get an undefined expression. So we end up with something here called a vertical asymptote. And those happen anywhere where you have a value that's not in the domain of the function. All right, so let's take a look at a couple more of these rational functions. So I'm going to start by giving you that they all contain vertical asymptotes, these next couple of functions. And we're going to determine their locations. And we're going to have to do that by factoring the denominators, because right now it's not obvious to me that this can be 0. And it's not obvious to me that that can be 0. And what I need to do is I need to figure out where these functions will be 0. And I can do that by factoring, because I'm noticing that this is just a quadratic expression. And I can factor that quadratic expression using double bubble or the AM method. So x squared plus 5x plus 6 can be rewritten as the product of two factors. I know that they're both going to begin with x, and in order to figure out what goes in the b spot of each of these factors, I'm just going to make a list of the factors of 6 and pick the 2 that add up to my b value. So plus 2 plus 3. So what this means then is the g of x could also be written as 4 times x plus 2 times x plus 3. It's the same thing. And the reason that that's useful is now we know that if x were to be -2, this would be 0. And 0 times anything is 0, so that would cause the whole denominator to be 0. The other number that would cause this would be negative 3, because that would make this factor 0, making this product 0, causing the denominator to be 0. So I'm going to say that my domain of this function is, again, all real numbers when x is not equal to negative 3 or negative 2. Because I have to throw those two out of the domain. All right, and now with h of x, I'm going to do the same thing. I think it's helpful in these cases to rewrite this as x squared plus 0x minus 36 at first. But we do have a quick factoring method that helps us here. So I make a list of my factors of negative 36, and I pick the two that add up to 0. That'll be 6 and negative 6. And what you'll notice then is I'll get x plus 6 and x minus 6. Hopefully you remember this as a difference of squares. If this is a perfect square and this is a perfect square and we're subtracting, then our factors will always end up just being the square root of your a term plus or minus the square root of your b term, right? So it's a pattern. Hopefully it's not new. But what we've learned here is that this could be rewritten as x plus 4 over x plus 6 times x minus 6, which means that our domain is, again, all the real numbers, but we have to throw out negative 6 and positive 6. And the reason we're throwing those out is because if I used negative 6, this term would become 0, making this product 0, making the whole denominator of this rational function 0. And 6 would do the same thing with our second factor. All right, so what we're going to do now is we're just going to sketch some rough behaviors of f of x, g of x, and h of x. And we've already got f of x over here, so we've got the space to sketch g of x and h of x below. And what we're going to do is we're going to graph it in the graphing calculator and then sketch it. So before you come in tomorrow, what I'd like you to do is to sketch those two functions roughly, and you may be able to try to figure out something about the behavior of those functions right now, just based on what we've determined already. But I'm just going to say that for g of x, you should at least go to 1, 2, 3, 4, 5 in both directions on the x-axis. And for h of x, you're going to want to go to about 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. So try to sketch those on your own. When you come in tomorrow, we'll see what they end up looking like when they're completed graphs. It obviously doesn't have to be perfect, but what I want you to do is just take these two functions, throw them into Desmos, and observe their behaviors. Something about those behaviors is unique enough that you're going to need to sketch those components here on the graph.